So as a lot of you have started working on homework have discovered, most of the homework problems relate to the implicit function theorem rather than the inverse function theorem. So I want to do the implicit function theorem today. I didn't want to do them both in one day and have you guys get them completely confused. So I did separate them. I do want to finish up with an observation from the inverse function theorem. And later in the week we shall do the proofs. And for one of the homework problems, for two of the homework problems, you actually need to know part of the proof. So, okay, so what did the inverse function theorem say, just to review?
If a C1 function that has the Jacobian matrix non-singular at a point, then
an open set in a
Okay.
then Jacobian is non-singular, then the neighborhood of that point is inverted in both U and f of U.
So if the derivative at A is non-singular, then there are neighborhoods V and W of A and f of A, respectively.
Where f of
And
a C1 function G
C1 function G
from
mapping
W to
W
V
to V.
such that G is the inverse of F,
So the
limited to V.
So G is the inverse of the restriction of F to V. And we also had the chain rule condition on what the derivative of G is in terms of the inverse. So remember, this picture was that you had some domain of F, and we said if the derivative of F at A is non-singular, then that means the best linear approximation of F is non-singular. So it ought to be the best linear approximation of the inverse. Its inverse should be the best linear approximation of what ought to be the inverse. So f of A goes somewhere here. There might be lots of points, and this is why I did that example yesterday. You might have various points that all map to f of A. But what you are guaranteed is some neighborhood of f of A, which I call V, and some neighborhood of f of A, which I call W, so that this is a one-to-one onto mapping here. You can go backwards in a C1 way. So remember that this notation meant this is the function. I didn't write this down yesterday, actually. This is the function that just eats points that are in V. You've just restricted the domain to be points of V.
And how do we know G is onto and is...
Well, that's part of the theorem. So as you will see when we do the proof tomorrow, what we're saying is you can actually find, say, a ball around A that maps one-to-one to some open set around f of A, and that's how you're going to define it. You're going to say, I take anything here and map it to the unique point from V, from the ball that maps to it.
So we're all inverses bijective?
Yes. So notice it's important to say that this is the inverse only once you've restricted it, because as we saw in the example yesterday, if you had a different green point that went to f of A, obviously there would not be an inverse function. But what we're saying is if the derivative at this green point is likewise non-singular, there's some neighborhood of it, and we can construct, say with a different neighborhood here, an inverse that goes to there. All right, so here's a consequence I want to point out. If you have a function say Rn to Rn, suppose you have a function from Rn to Rn that's C1, and whose derivative is everywhere non-singular. So we had an example of such a thing yesterday. So we had an example. The second example yesterday was an example of a function where the derivative was everywhere non-singular, but the function was badly not one-to-one. But I wanted to still draw the conclusion that F maps open sets to open sets. Can you give me an example? So we haven't talked about this idea before. We've talked about continuity relating open sets. That if you, for every epsilon, there was a delta.
Or something like the image of an open set for a continuous function is also open.
No, that's this.
Oh, that's that, okay.
What we had in chapter 2, if you paid attention to it, was that the pre-image of open sets was open.
Okay.
If you had a continuous function. This is the opposite. We're saying open maps to open. Can you get, yes sir?
Well, is this, I guess, is it because, like, every point in U maps to, like, a neighborhood in W? And since
Yes.
every point in W has a neighborhood around it, it's all, like, open, so every point in W is open? Or,
Yeah, I mean, you've got the right idea. You're not saying it 100% correctly, but that's the right idea. So the proof is going to be just saying, what did this tell us? But before I do the proof, can anyone give me an example of a perfectly wonderful function you know from 9th grade? Mapping R to R.
Y equals X. Y equals X squared.
what is it?
Does that function map open sets to open sets? So what does the graph of this function look like?
Yeah. No, it doesn't.
You zero has
So
there's
not
no
that
point.
So if you, as everyone knows, that's the graph.
We should use sin X.
Okay. So what happens? Well, if I take this open set, it maps to all the y values that go. I had to make life difficult, didn't I? This open set, it maps you to all the y values between here and here. So it maps you to that open interval. So this open interval of x's maps to this open interval of y's. But you guys who all suggested this, what should I look at? What open set should I look at?
An interval
Well,
containing the
zero.
origin.
An interval containing the origin. If I take an interval that contains the origin,
As an integer.
what does it map to?
A closed
Zero
set that's
to-
not open.
It maps to something that looks like that. It's not open, it's not closed.
It's gray.
It's cloven.
It's not,
Cloven is better.
it's door-like. Right, so what caused this to happen?
The derivative is
The
zero.
derivative changes sign.
That is not on food.
Well, but in terms of the hypotheses, what failed?
The derivative is
The
zero.
derivative was zero at the place where it folded across. This is like the example we were doing yesterday, where I talked about folding. What are you doing here?
That's got canceled. So I figured that was wrong.
They haven't missed enough already?
Yeah, seriously.
Jeez. Well, welcome. Okay, so it's because the derivative is vanishing and allowing the function which was going a certain way to turn around and go back the same way again. So, right, the y values as you come into the origin are coming down. The derivative is zero, so you can turn around and you go back up. So it's like the folding I was talking about yesterday, where you're taking the x-axis and folding it across the origin when you do the squaring map. So these things are mapping to the same points. So you're collapsing. The map is taking the x-axis and folding it across the origin, and gluing it together.
And this were like f of x equals x cubed.
Mhm. So that isn't a counterexample. It does map open sets to open sets, even though
Right.
the derivative failed to be non-singular.
Okay.
So I'm not saying if and only if.
Okay.
So cosine and sine.
So Cameron suggested sine or cosine is the exact same phenomenon. So the sine function, if you took an open interval around pi over 2, you would have the exact same phenomenon that that open interval mapped to a half closed, half open interval.
You would have it closed if you could have it completely closed. If you go from 0 to 2 pi.
All we're discussing is doesn't have to map open sets to open sets. The answer is no. All right, so this is actually a very important consequence, and I may actually do something with this later this week, depending on how time goes. But so what Lama was talking about, why this should be true. If I take, what does it mean to say F maps open sets to open sets? Well, I have to take some open set here and look at what F of it is and argue that it's an open set. So let's let, I'm running out of letters. Can't use U, V, or W.
X. Yeah, that seems.
X never feels open to me. But O.
A, B.
It
Yeah,
looks like 0.
groovy.
Looks like a matrix. T.
Okay. Why not B?
T.
D.
Yeah, T's very close. I don't know. T's very close.
Let's script O be an open set.
That's what we're using.
We want to show F of O is open. So how do you show some set is open?
Let's just point in it.
For any x one.
Okay, I don't want to use X, but so take any point in F of O. Let's call it Y. What do we want to do? So here I have the picture here. I'm picking a Y that's somewhere over here. I want to find a ball around it that's contained, right? What does it mean that Y is an F of O?
There's a neighborhood.
No.
Oh.
It means there's some point in O that maps to Y.
So there's some A in the open set O, so that Y is F of A. Does my choosing the letter A help?
Oh, like an
No, I'm not going to do that. Well, we know that for every A, the derivative is non-singular. So by the inverse function theorem, there's a neighborhood of A and a neighborhood of F of A, so that F maps this neighborhood one-to-one and onto that neighborhood. So by the inverse function theorem, there are neighborhoods V of A and W of Y, right? That's F of A. So that F restricted to V maps V to W one-to-one and onto. So that does it. Because that means I can take a ball inside W that's centered at F of A, and it will be inside of F of O. So make sure, shrink V if necessary, so that V is contained in O. So if you have an open set V and an open set O that both contain A, how can I assume that V is actually contained in O? What can I do? Almost. Take the intersection of those two, right? That will still be open. You guys proved that at home last semester. Okay. Choose an epsilon so that the ball centered at Y of radius epsilon is contained in W. Well, why can I do that? Well, because W is open. So there's a ball centered at Y contained in W, but then W is contained in F of O because V is contained in O. So all the stuff that V maps into W, all these points are in F of O. Because F of O contains all these points plus extra stuff. That means F of O is open. So because you have the inverse function theorem, which gives you an open set to wriggle in here, that means that because this open set is mapping one-to-one and onto, you have an open set to wiggle in the image. That makes the open. So wherever any open set you took here, the image of it has wiggle room in it. That's what openness means. Lama, did you have something? Okay. So this is actually important in higher mathematics as well, but I'm going to try to do something later this week where we use this. Okay, implicit.
They'll be there till his next birthday.
Yeah, right. So we saw the implicit function theorem last semester, and I promised you'd get to see it again. So here we are. Now I'm going to state it in generality. We're going to get more practice using it, and we're going to do lots more examples as the week goes on. So, inverse function theorem, remember we're mapping n dimensions to n dimensions. You may or may not recall from last semester that we wanted to say, as you did in beginning calculus, you write down some equation of a bunch of variables, and you want to know, does this equation implicitly define y as a function of x? So remember the example we talked about last semester in detail was this equation. And you asked, does it always define y as a function of x? No, but it does locally as long as what?
You're away from
You're away from when
As long as you're away from the endpoints, then near any point on this curve, you can, in a neighborhood of that point, say this is the graph of a C1 function, y is a function of x. So these were the bad points. So something bad happened that allowed us to rule those out. So here's the general statement of the theorem. All right, so there's a lot of notation, but it isn't so. I'm going to set it up so that it is actually helpful to you in the long run. So suppose, and I'm going to use capital F instead of little f, just to remind you that we're doing a different theorem. And now we're going to take an open set in n dimensions still, but we're not going to map to n dimensions, we're going to map to m. And now we're going to say n is at least m. And of course f is going to be C1. Now here's what I'm going to do. I'm going to write points of Rn, or U, in the form x, y, with vector signs on them, where x lives in n minus m variables, and y lives in m. Okay, so I'm breaking my variables in n space up according to how big m is. And here's what I'm going to do. Suppose we consider the point x naught, y naught. And suppose f sends that to, say, the 0 vector in R. It didn't have to be 0, but I'm going to say it's 0. And we want to consider all the points that f sends to 0. So I'm going to call that m, foreshadowed. Let m be the 0 locus of capital F. So it's going to be the set of xy in U, so that f of xy is this constant 0. So this is looking analogous to saying, here's f, and I'm taking a constant value 1. Well, I can rewrite that as that function is equal to 0. I'm looking at the x's and y's where this function is 0. That's what I'm doing here with this m. It's a level set, exactly. I'm looking at the 0 level set of this function, capital F, and I know this particular point is in there. So here's a schematic picture for you. This is Rn, and this is Rm. So here I have n minus m variables. Here I have m variables. So these dimensions are matching. Now, it is confusing because this dimension looks the same to you, but it's not. Your eyes are not working right. This is really 5-dimensional, and this is really 2-dimensional. This is 5 also.
Wait, so is the F just turns it into an RM line? It doesn't like.
Right? It's mapping you to m. These are the same. This dimension's different.
But there's no like second dimension.
Because I have only Rm.
Okay.
And what I'm doing here is I'm fixing 0.
Oh, right.
And I'm looking at the pre-image. I'm looking at all the points that map to 0. And it's going to look like some weird thing that has the same number of dimensions as this. Intuitively, why is that right? Think about linear algebra. You have n variables and m equations. That cuts down your dimension, each one, if they're independent, m times. So you're left with how many degrees of freedom in the 0 set? N minus m, which is this dimension. So here's my point x naught, y naught. No, it's actually at least. Well. And what I'm saying is, I can find open sets or neighborhoods v of x naught and w of y naught. So here in this picture is a neighborhood of x naught and a neighborhood of y naught. So that if I look at the part of m that's inside v cross w, so I've got a rectangle that I can draw here that looks like this. If I look at the part of m that's in that rectangle, then I'm going to say that I have a C1 function phi from v to w so that the level set that lives inside this rectangle. So the part of M where the x coordinates in V and the y coordinates in W is exactly the set of points x, phi of x. So I'm saying you can locally represent M, this level set, as a graph of a C1 function from n minus m variables to m variables. That's the implicit function thing.
What's the letter at the end? Is that a
Where?
M? It looks kind of like intersection. That intersection.
It is intersect. Here?
Okay. Okay.
This means the part of M that's in this rectangle.
Yeah.
So it is the intersection. And then the end of the theorem is the formula that you all know for implicit differentiation. We said phi is C1. Oh, well, I left out the hypotheses. Oops, roll tape. I left out a hypothesis. You guys didn't catch me.
Sorry. Shocker.
Right? We needed to rule out the bad points.
Oh, right.
Yeah, look, there's a rectangle that's
So the,
Yeah, so we better have some hypothesis here. This is so asterisk. Insert most important hypotheses. This is 2 days in a row. Asterisk. Most important hypothesis. Well, what's the... So don't you ever forget this when I ask you to state the theorem.
You're gonna ask us to say the theorem?
You'll never forget it. What's the hypothesis? Well, we want to rule out that the level set is bending back on itself. That would stop it from being a graph. You want to rule out these points. Those points occur when the partial derivatives of f with respect to y vanish. So I'm going to suppose the most important hypothesis was that if I take the y partials of f and look at them at my fixed point x naught, y naught, that is non-singular. So that's the analog in this example of saying the partial respect to y is 0 at those points. So I'm assuming that if I take the y partials, I get a non-singular matrix. And you say, what in the world does this notation mean? Well, df it's a what by what matrix.
2 by 2.
Mapping n to m, so it is m by n, like we've always tried to have. Well, I've written my variables in 2 pieces. So I differentiate first with respect to all the x's, and I'm going to write that part of the matrix this way. So when by the partial respect to x vector, I mean the first column is the partial respect to x1, the second column is partial respect to x2, and so on. And then you get to the partials with respect to y. How many y variables are there? How many?
just M.
M. So what shape is this part of the matrix here?
Square.
Square. It's m by m. So that's why I'm saying that part is non-singular. Then you can locally write y as a function of x. And then, now my conclusion is that if you wanted to compute the derivative of phi, the implicit differentiation formula, which we actually talked about last semester, but I'm going to do it again for you, is you take minus this non-singular matrix inverse, and you multiply it by the matrix of partial of f with respect to x. So the derivative of the implicit function is given by this matrix multiplication minus the inverse of the invertible part times the part that's differentiating f with respect to x.
which is an m by n matrix times an m by n minus n.
Right.
What do you know what sound this mean?
So this is m by n minus m, which is appropriate because how many x's are there? N minus m. So that's how many columns this matrix has. And it has the same number of rows as F is supposed to, so it has m rows. All right. So I'm going to do examples so you see what's going on.
So why does df/dy vector being non-singular guarantee? I'm confused how that relates to the function bending in on itself.
It's basically saying that you have pivots in the y part of the matrix. Right? If you think about this matrix, if this part's non-singular, it's the opposite of the way we did echelon form last semester, where we always tried to put our pivots over here. But we're saying you can find m pivots in this part of the matrix.
Okay.
Those become free variables. When you have pivots, they become the free variables. No. I said it exactly wrong again. This is bad. The pivots are the dependent variables that you solve for in terms of the free variables.
Right. So we would just say,
So we're saying locally, linearly, you can solve for the y's in terms of the x's.
so we would just say df is non-singular except it's not square, so we can't say that.
So we're interested in the part that is coming from the variables you're trying to solve for.
Okay.
So you have m equations, you're trying to solve for m of the variables in terms of the remaining free variables. That's the way we're trying to do it.
Notation question. Why do we have a vector sign over the neighborhood W?
Over whom?
The neighborhood W,
That would
in the middle.
typo. These Tuesday, Thursday classes are getting long for me.
You've been here 2 per week now.
I know. Well, we're only going to do that this week and then one more. Okay, so, all right, so big theorem, most important hypothesis. Notice that when we talked about the circle example, so I'm going to do a bunch of examples, but example 0. Suppose we had our circle equation. We set this equal to 0. What did we say? Well, we said when you took the partial. By the way, I'm not writing vector signs on anybody here because we're mapping R2 to R1, and x and y are scalar variables, and the output of f is a scalar. What's the partial respect to y? All together. So when is this 1 by 1 matrix non-singular?
Y is not 0.
So as long as y isn't 0, you can locally write the level set as a graph where y is a function of x. So where this matrix is becoming singular is where the trouble points are. But as long as you have non-singularity, you can locally write it as y as a function of x. Okay, let's do a bunch more examples. So one of your homework problems, the ideal gas law is reappearing and generalizations of it. So you now finally get to understand that webwork problem from last semester where you got the product of those partials being -1.
Yeah, and didn't the negative, is that kind of where the moreover d phi of x, is that
That's a negative.
It's the same negative that we...
That's the same negative. But try to stay positive about it. All right. Suppose I took the function of x and y that said tangent of y minus x. And I looked at the 0 level set of that. So what does that look like?
Bunch of, it's like the graph of the tangent function, but
Yeah.
you're graphing x as a function of y.
You're graphing x as a function of y, so instead of doing the usual tangent function, you're doing something like that that now has horizontal asymptotes instead of vertical ones. Agreed?
Yeah.
And if you want to be pedantic, those asymptotes are occurring there, and then the graph repeats, right? So the domain of this function has to exclude where y is an odd multiple of pi over 2, if you want to be pedantic. All right, can we locally write y as a function of x?
Yep.
I mean, can you write it globally?
Yes. No, not everywhere.
If you use certain notation.
You certainly can't write y as a function of x. It fails the vertical line test. It's like what we were talking about yesterday. But if I take a point where some partial derivative isn't 0, I'm supposed to be able to locally do it. Well, let's, so now of course I've ruined the function. So what is the partial, so is FC1?
Yes.
Sure. What is df at a point xy? I'll do the hard part. You do the easy part.
Secant squared y.
Tell me about secant. Tell me more about secant.
One
It
of
is
the
whatever
cosine.
cosine squared.
It's secant squared over cosine squared. Is that ever 0?
No. It can be in
No,
under
it's
five.
never
It can
zero.
be
It's never 0. So at any point in the domain of f, this is non-zero. So what does that tell you? It tells you that at any point on this 0 level set you pick, you can find neighborhoods. And in fact, as long as you take the neighborhood, you can do it. In fact, what can your neighborhood be? It can be all of R here, and then a small neighborhood, a neighborhood that goes like this here. Orange and blue. So your neighborhood would actually look like this. For that point. You actually can get a y globally as a function of x, provided you restrict the y values. If I had started at this point, you would now have it, still you could do it for all x's, but you would have a different restriction on the y's. And in fact, so if y is in the interval from negative pi over 2 to pi over 2, what is the famous function that y equals?
Arctan.
It's called arctan.
Oh, something.
And if y were in this interval, what would I do?
You
So
subtract
subtract
Don't you just subtract pi?
Yeah.
Okay, just subtract pi from this. All right, just to point out what this formula is saying for taking the derivative, what is phi prime of x?
Negative.
I'm supposed to take negative. I'm supposed to take the inverse of this.
Cosine squared y.
So I'm supposed to take cosine squared of, but I'm supposed to do it at what y? I'm supposed to do it at the y that's phi of x. Right? You're at the place where x equals x and y equals phi of x. And then you take that times with respect to x of this function, right? So this was the inverse.
Wait, wouldn't the derivative with respect to x of -1 be 0?
That is a derivative.
This is the
Oh,
derivative.
right.
So if the minuses go away, I get cosine squared of arctan of x. You guys remember how to do this? You're saying, I'm thinking of an angle theta whose tangent is x.
That means x squared plus 1, or yes, root 1 plus x squared.
Now, in principle, you have to make sure it works when you're in, for any theta in the appropriate quadrants, but it does. And there you go, folks. There's the derivative of arctan. And it's actually the same proof you learned in your baby calculus class, except you never wrote partials, but you did implicit differentiation. And that's where this formula comes from, as I will remind you on Thursday.
What happens when y equals pi over 2?
It's not in the domain of the function.
It's just not
The
in
F is, that's not in the domain, right? You have to be in the domain of capital F, so y can't be an odd multiple pi over 2.
Why do we put phi of x in for y?
Well, because I was sloppy here and I didn't tell you where to evaluate these. Where are you evaluating these partials? You're evaluating them at the point x, y.
Which is phi of x, x phi of x.
Right. Right, because you're at a point of that form. Right. Okay, let's do a more interesting example. No, maybe this isn't more interesting, but. All right, now I'm going to do capital F mapping R3 to R2. So I want to break my function up, I want to break R3 up into x and y, where x is 1 and y is 2. So I'm going to actually write it that way. Some of you were complaining in my office yesterday about horrible notation, but I'm doing this rather than x, y, z, just to help you think about how we've broken the function up, the domain up in terms of x and y. Okay? So it's sort of yucky, but it's actually going to help you think about it. y1 is going to equal x squared, and y2 is going to equal x cubed. And I'm going to look where this is 0. So y1 minus x squared is going to be 0, y2 minus x cubed is going to be 0.
So, just the graph like up there, the first one did, it would be R1 and R2.
Mm-hmm.
Okay.
So what does this level set look like? It's a subset of R3. If I look where f is equal to 0, what does it look like? Remember this notation from pre-image of 0. That's the set of points where you hit 0.
Some curve defined by the intersection of two surfaces.
Okay. So you're going to set y1 minus x squared equal to 0, and you're going to set y2 minus x cubed equal to 0. Now, do you actually have a picture of what that curve, what this actually is?
I feel like it's like the parabola, but then the height of it's determined by a cubic function.
Good for you. So I'm not sure we've done this example in this class. I did it in the other class recently. So this is going to be actually the set of points what? Can we actually write it as x phi of x? Can you write this as the set of points x phi of x? Well, let's see what the theorem says, and then we'll try to do what Reese was doing there. So let's write down df. X we're mapping to R2, so I have to have a 2 by 3. 2 by 3. Okay? Tell me the first row.
Negative 2x, 1, 0.
Tell me the second row.
Zero.
Ask yourself,
So.
is the df/dy matrix non-singular? Think really hard.
I need to prove that.
Okay. Everywhere non-singular. So we ought to be able, around any point, we ought to be able to write y as a function of x on this thing. Well, duh. What's phi? What's y1?
X squared.
What's x? What's y2? So you're graphing this function of x. So m is, in fact, globally. The theorem only tells you locally, but in fact, you can do it globally, as I just did. M is the set of x, x squared, x cubed, as x varies over all the real numbers. And Reese was actually gesticulating what that looks like. This is actually a famous curve called the twisted cubic curve.
Oh, we did talk about this in class.
Did I, last semester?
And we drew it in different projections.
Oh, okay, well then we did it. Okay. So, see notes from chapter 2. Or the book. So, okay.
So we got phi of x equals x squared x cubed from
From these equations.
okay.
It was sort of boring. I'm going to do one that's harder now.
Alright, thanks. That's exactly what I was thinking.
Alright, we'll do one more example and then call it a day for today.
And just for clarification, we're gonna have this Thursday class and then next Thursday class?
I'm thinking we'll skip next Thursday partly because our videographer, but I think you guys, it's too much to do 2 weeks in a row.
Seriously.
So we'll do the other one either before spring break or after spring break. That narrowed it down. We could do it during spring break.
This level is going to be.
We
like-
laugh.
Seriously.
I have to be in
Patty,
Tennessee.
come film me at my house.
All right. So here's another, what am I up to? Number 3. So now I'm going to do, again, I'm going to do x and 2 y's, and then we'll do one more example tomorrow where there's 2 of each. So here's I want to write down 2 equations. One is x squared plus y1 squared plus y2 squared minus 2, which is going to be 0. And the other one is y1 squared plus y2 squared minus 2y2 equals 0.
I think that's. The top one's a sphere.
Careful. So, sphere of radius,
Root 2.
square root of 2.
And then you have each circle in the y1, y2 point.
So I'm actually going to draw it with x this way, even though you don't like that. And I'm going to put y1 and y2 here.
Wait, are we just allowed to
But
do that now?
But it's not centered at the.
Can we just like do that on our
Doesn't
own?
minus 2 shifted down?
Just like,
Not makes me
Well,
Turn it lower.
I can label them any way I want to if I want to make you see the picture better. Now what is this? What is y1 squared plus y2 squared minus 2y2 equals 0?
It's a circle that shifted.
It knows the cylinder.
Well, you're in the y1, y2 plane, Cameron is saying it is a circle that's off-center. Centered where? Oh, actually,
centered
At
out.
0, 2.
0, 1.
Is there a square root of 2?
I think it's root 2. Right?
Yeah,
Zero.
root 2 is square root.
0, 2.
I don't know, it's somewhere.
your main wins this battle.
you named the one.
complete the
okay.
triangle, that's right.
Complete the square, right?
Yeah.
So you have a cylinder that's centered here of radius 1. So if the radius of the sphere was square root of 2, so the cylinder is going outside. And if we look at capital F equals 0, we're looking where those two surfaces intersect.
And we did this last semester, right?
We did something like this last semester. Did we do this
You have an
exactly?
incredible memory of last
I
semester.
know, really.
We looked
Where
at
did I keep it?
persons, I don't think we looked at the
Yeah.
exact
We
equation.
might have actually done this one.
I think that's
Does that mean you know everything and I should quit?
Yeah.
No.
Rest of the semester, we're done.
the circle is inside?
Is that an actual, is that a circle?
I didn't mean that as a put down.
Is
Is that meant to be a circle?
Wait. Are you saying this picture's wrong?
Yeah.
No,
Put
no.
it to his paper then.
Square root of
Square root of 2.
There's less.
Comes out here.
It's bigger than square root. Oh.
Yeah, so
Oh,
that's why
oh,
the center
yeah,
is in this.
So you mean it's wrong now.
Yeah.
Just to be sure.
She
We
got
have it on
cocky on.
tape too.
That'll be a good time
Getting
rest this semester.
All right, so let's see what the theorem says. df. All right, what by what? It's again 2 by 3. I'll do the hard part.
You always say you do the hard part.
You've always been very
I always
generous.
struggle with the easy stuff.
I know,
So,
but I think this time you can manage.
2 by 1, 2 by 2. 0.
0.
0.
2
2
by
by
1.
1. 2 by 2 minus 2.
So if you'll allow me to factor out a 2. More interesting than the last one. Now we want to look at the course with respect to y part of the matrix.
It's not a 4.
That's a 4.
We're taking out 2 rows.
It's a matrix.
This isn't the term.
I'm still confused. I don't know. So we don't take.
We're not taking determinant of a 2 by 3 matrix.
Oh, yeah.
That's open. It's a matrix.
Yeah, I'm kind of confused about how you do that.
Well, let's just
It's like,
Oh, okay, yeah, I
it's
got it. I got it. I got it. Yeah.
Okay.
There's so many things going on.
All right, so I'm asking myself,
Oh,
is this blue matrix invertible? Not singular.
look at the determinant.
Look at its determinant. So df dy is this matrix, and I'll put a half there just in case someone's watching. y1, y2 minus 1, and the determinant is, oh, this is hard. So what's the determinant?
Not pretty.
Y1, Y2, minus 1, minus 1.
Negative y1.
Minus.
Yeah.
So as long as y1 isn't 0, I can find an inverse of that matrix, and that means locally I can write x as y as a function of x. So what is, so away from points with y1 equals 0, so this is on M. We can locally write M as y equals phi of x. So what? So I might actually even bring in the computer and show you this, even though Daniel remembers it perfectly from last semester. What is the intersection? What's this curve when you intersect these things?
Isn't it y1 not equal to 0?
Sector.
Oh my god.
Away from.
Oh, okay.
Yeah, but thanks for making sure I didn't screw up.
It's like a balloon with a pipe with balloon in it.
It's a
It's like a rubber
curve. How do I,
band. It's like a rubber band that you've sort of bent a little bit.
or it's the edge of a Pringle.
Yeah.
Oh yeah.
It is almost lunchtime, right?
speaking of.
So what happens? Well, where is y1 equal to 0?
On the Y2.
That this thing is symmetric about the x, y2 plane. There's a part that comes out in front here. And then it goes down to the bottom. And then it comes back up the back. It does something like
This is
that.
because if I took and smashed the graph in like this, it'd be doing.
So what's happening? Well, when at the high point here is when x is at the maximum and you can't locally write the thing as a graph there. Right? Because it's exactly like the circle case where this is on the axis. Near there, there are two y's for every x. But everywhere else, except for these 2 points, you can locally take this piece where you're giving y as a function x and you do the back piece for y as a function x. I wouldn't want to write down the explicit equations in this case, but I can. It's again, it's a mirror image thing, which is folding
And then start not really
at those 2 points.
and then kind of cylinder things.
Okay, so
And then take that piece out.
this curve actually is sort of interesting, and you might even encounter it later in the course.
And
So it's
It's
part of the
just like a
cylinder.
failed threat.
Question to ponder,
It's
Pick
harder.
a
what
hole.
happens, so Daniel's going to say we did this last semester too.
It's helping me a little.
If we replace the 2 in the first equation by a 4. So suppose I made this,
It would just be negative.
I had mathematics pulled up and everything.
And it's gonna,
isn't
Well,
all
wouldn't it
that
just-
a file of interest?
Probably.
so what happens in that case? In that case, the orange sphere comes out and it hits exactly here. And since Jackson remembers it perfectly,
We get a figure 8.
you get a figure 8 curve. And so you actually do not get a smooth manifold. That's coming soon.
But would that 4 impact any of what we did with regards to like d of f? That would all be the exact same?
This is all going to be the exact same, but what you're going to find is that that's an extra place where y1 is 0 on the graph.
Oh.
Here,
Ah,
here where you crossed the y1, y2 plane, the 2 points were separated.
Mm.
As you make the radius of the orange sphere get bigger, these 2 points where you're crossing come out to here. And it's a point where y1 equals 0. So if you actually plugged y1 equal to 0 into these equations, you would be able to do algebra and see the only places it happens is if you put y1 equal to 0 and solve these equations, you're going to see you're only getting those 2 points.
is that top point not on the x-axis?
No. Oh, wait. Yeah, what I drew is wrong. Yep. Yep. Ken's absolutely right. I was distracted by my own picture there. I don't know what I was saying. Yeah. So, yeah, you're right. I apologize. Right, so it's going up, coming back down the back, and then coming down here. Yep, that's 2 days in a row I've done stupid
so
things.
what happens if the
Now
ring
that
of
I
the
can
circle?
I wish
see
my
better.
definition of stupid was
So
I can see that
put
better.
y1 equal to
Yeah.
0 in
That
the
makes more
equations. You get x squared plus y2 squared minus 2 equals 0. And you get y2 squared minus 2y2 equals 0. So, let's see. So what happens?
So it's almost like the
So
grids on a tennis ball.
y2 is either 0
Okay,
or
that's how it might be. For a baseball shot.
2. Now, can y2 equal 2? If y2 were 2, the first equation would say x squared
-2.
plus 4 minus 2 is 0. So this can't happen.
You can see it on the graph.
You can see it on the graph. But I was trying to actually do the algebra since I messed up the graph the first time. So the only way it can happen is if y2 is 0, and then this equation says x squared is 2, which means it's exactly what Ken said. You're at y1 and y2 both 0, and you're at the 2 top and bottom points. Okay, we're done.